I want to thank organizers for inviting me. It's a great opportunity to participate in this nice program and to lead the discussion on soft theorems. So I also want to mention my collaborators who also worked and contributed a lot in this whole research project. So it's Temple He, Daniel Kapek, Prahar Mitra, Sabrina Pastersky, Andy Strominger, and Sasha Zheboyedov. And I also want to recommend Andy Strominger's lecture. So he gave a beautiful lecture on basically soft theories, asymptotic symmetries, and gravitational memory last week. So I highly recommend you to also watch this lecture. So my today's discussion will be, in some sense, a little bit complementary to what Andy did in his lecture. So he mostly discussed this new gravitational memory and the relation of gravitational memory to both soft theorems and asymptotic symmetries. So I instead today will focus on this part of relation of relating soft theorems and asymptotic symmetries. But I will, for some, I'll probably use like this memory effect to argue that certain asymptotic symmetries which may look like a trivial transformations or something like a gauge redundancy are actually related to some physically measurable effects, and that's why they are not something like a pure gauge or some bad gauge choice with some leftover gauge redundancy. So that's why this corner of triangle will be important for me as some kind of at least physical way of actually testing both sides of correspondence. And I also want to copy this kind of small list which Andy had in his talk, and that's kind of basically a summary of various theories and cases where we tested correspondence between soft theorems and asymptotic symmetries, and in some cases relation to this memory effect. So basically it's some simplest. So the simplest case is obviously some Maxwell theory coupled to some massless charged particles, but it also can be generalized to Young-Mills or gravity coupled to matter. And also it seems that it's possible to generalize it beyond the level of massless matter to include massive particles. So also I will talk about, hopefully I'll get to subleading soft theorems. And basically subleading soft theorems means that there is a subleading effect, and I will basically explain what this classification means, but generally it's some expansion in the soft theorems, and this correspondence was tested for both leading and subleading terms. Also it seems that at least leading story can be discussed in dimensions higher than 4, so and that's because usually we think that all this nice infinite dimensional asymptotic symmetries, it only happens because of some low dimensions and stuff, that certain things are just, the dimension is too small, that everything should be related to everything. And it seems that actually leading story kind of goes smoothly in dimensions higher than 4. And that agrees with this kind of prediction from a soft theorems, which can be formulated in an arbitrary number of dimensions. Also, it seems that this story can be extended to supersymmetry case, where we also know all these beautiful soft theorems in n=8 supergravity and n=4 super-Young-Mills. It seems that you can also properly extend asymptotic symmetry to include supersymmetry as well. So I wouldn't probably say much about sort of quantum correction. So basically, most of my discussion will be fairly classical, but there is a hope that the sort of quantum stories somehow fit nicely, either as some kind of anomaly if the symmetry is broken on quantum level, which still gives some interesting word identity, or there might be some formulation of there might be some alternative definition of S matrix in quantum gravity, which allows you to also somehow incorporate quantum corrections to subleading soft theorems. Okay, so that's kind of overview of where we're going. So I will that was introduction. So I will start with just going through the simplest example, which happens to be just Maxwell's theory coupled to some charged particles, to some massless charged particles. And then this example can easily be generalized to leading gravity soft theorems, which is probably the most interesting case. And then after we will build up some intuition and some notation, I will hopefully explain what happens in subleading case. So that, and then if we have some time left, we can talk about like even further generalization to high dimension supersymmetric case and apparently string theory. Okay, so let me start with the Maxwell theory. So basically the idea is just to study Maxwell's theory in four-dimensional Minkowski space, and we just have U1 gauge field, which is coupled to some massless matter, which is described by some gauge current. So basically, let me look at some scattering amplitude. So let me assume that I have these on-shell particles, which with momenta pk, and for simplicity, I will assume that they are massless. And let me look at amplitude where I have some number of these charged particles and a single photon with polarization epsilon and momenta q. So q squared is 0, so everything is on shell. And let me take a limit q goes to 0 for this amplitude. So apparently, I think it was low in 1954. Basically considered this question for the first time, and he showed that apparently there is some universality in this limit q goes to 0. That first few couple of terms in small q expansion are actually independent on internal structure of a diagram and can be expressed as some operator J acting on external data, which may include momenta and some internal degrees of freedom, like some polarization, spin, and stuff, and plus some. So in case of Maxwell's theory, it will be corrections of order q to the 1. So the leading term, so this J also has expansion, so there are two terms in this case. So one term is order 1 over q, which we'll call leading soft theorem, and often is denoted as J0. So it depends on polarization, q, and external momenta. And there is what we call subleading term of soft theorem, which is order q to the 0, which depends on polarization, momenta, and also some spin data.
Just one more light here. You could turn on the middle switch.
Middle switch, okay, great. Yeah, thank you. Okay, and these extra terms, they kind of do depend on particular interaction between this massless particle coupled to H series. So J0 is given by following expression. So it's okay. Let me assume that E is just a coupling constant and 2k. Okay, some integral charges of my particles. So that's J0. Okay, and J1 has the following form. Okay, so there is E in front. So there is I in front of it because it has following structure. So J mu is the total angular momentum operator. And here I will use this as kind of usual convenient notation that ingoing particles has charge plus q and outgoing particles has charge minus q. So instead of writing two sums for ingoing and outgoing particles. Okay, so some of you probably are familiar with this derivation, but let me just sketch some kind of why do we have angular momentum here. So basically, this diagram is just given by a coupling of soft photon to external legs. So you have like some n external legs, and you can couple the soft photon to any of external legs, and since this thing is, this part is on shell, and when q goes to 0, this intermediate propagator also goes on shell, and that's why we have a pole in p dot q, and p dot epsilon is just a derivative which is just a derivative coupling which you have for coupling to a photon field. So now, if we go to a subleading term, then you will have two types of diagrams. So there will be some expansion of this diagram there will be some subleading contribution to this diagram. So it will be something like J0 acting on M with one of the momenta shifted by Q. J0 acting on K stack. And you can further expand it and get some kind of term QD over dpk. But there will be also a second diagram which will contribute when you have a coupling, a soft photon attached to some of the internal legs. And but apparently we also want this theory to be gauge invariant, so J0 and J1 better be independent on a gauge transformation for a photon. So I still have this freedom in shifting polarization. So J0 is invariant because of the charge conservation, total charge conservation, and for this thing, so that's a contribution from a first diagram, and contribution for a second diagram better be correcting this expression to something which makes J1 gauge invariant. And apparently you can correct it to just orbital angular momentum operator, so something like this, but we also need to add a spin part because only total angular momentum is conserved, and therefore this expression is also gauge invariant because of the antisymmetry of a total angular momentum operator. So that's sort of kind of simple derivation which was used by Law in 1954. So it doesn't require like any spinor helicity formally, and so it only relies on some gauge invariance and some simple consideration that the certain terms should combine into gauge invariant expression. So this logic can be used in a similar way in the gravity case. So in the gravity, there are actually three universal terms. So the leading soft theorem is just given by this expression. Some of it. The subleading one is it also so the I stands because J is anti-Hermitian, so that's why. Okay, and I should put like some kappa squared. Kappa. And the structure is very similar, so it's still you still replace 1p by q, and you replace angular momentum. So okay, and one remaining contraction. And sort of the last term, which is universal, it's like some kappa over 2. And then you replace both pk's by angular momentum. Yeah, and sort of gauge invariant. So this expression is gauge invariant. So the first one is because of total energy conservation. The second one because of total angular momentum conservation. The third one because of antisymmetry. Okay. So and today I will start with turning basically this J0 into some word identity. And then immediately you can see that this J0 can also be turned into a word identity. And apparently there is some similarity in the structure between J1 in both gauge theory and gravity, so we expect that sort of similar things, that there will be some similarity between the corresponding asymptotical symmetry groups. And apparently I don't have much to say about this subleading term in the gravity soft theorem, and hopefully I will explain why. So there is some relation why this part is hard. Okay. So let me now explain the second part of a correspondence, which is asymptotic symmetries. So basically, for example, in the gravity case, we have a notion of normal symmetry. So we say that if you have some vector field which preserves a metric, then it is a symmetry of this particular metric. So, and we can write it as mathematically in the following way: that v derivative with respect to this vector field of a given metric is just 0. So asymptotic symmetry is basically generalizing this notion to the following one. So let us, instead of considering one particular metric, let us consider a class of asymptotically flat metrics. So that's a matrix which, in some properly defined, so when you define what do you mean by far enough in Minkowski space, that they basically approach Minkowski space in some way. So just to make it more precise, let me just introduce some coordinate system which I will use later anyway, so just to make some formulas more explicit. So there is a way to formulate it in sort of nice invariant language, like following Penrose, using all this null infinity structure, like omegas and stuff. But for sort of our purposes, it will be just fine to fix some good enough gauge and work in gauge. Okay, so let me introduce the following coordinates, as I think called retarded coordinates in Minkowski space. So if I have this Minkowski diamond, then R is sort of this coordinate. The scribe plus region is the region of R equals infinity, and where in U, the scribe minus region, I need to do some coordinate transform to the scribe minus, and at fixed U and R, I just have a two-dimensional sphere which is parameterized by coordinates ZA. So if you want, you can think about like ZA as being Z and Z bar, which are usual complex coordinates in two spheres, then gamma. Then this gamma AB will have only single component gamma Z bar, which will be of the form okay. So in this gauge we can define asymptotically flat matrix. So that's just releasing Minkowski matrix. So the asymptotically flat matrix is a matrix which differ Minkowski metric by some subleading 1 over R power. So you can just start writing some subleading 1 over R powers. So that's like familiar Bondi mass, and you don't do any changes in R something term, which is precisely a gauge which you want to hold, and then you can have some subleading term R CAD DZA DZB, and so on. And you also can have DZA DB term. Yeah, so you can define precisely the class of asymptotic flat matrix, and then you just want to say that that asymptotic symmetries are just some transformations which will transform your metric by some subleading term. So when you apply it to a metric with subleading terms, only these functions MC and UA will be transformed. So that's kind of notion of asymptotic symmetry. So in context of Maxwell's theory, if you apply this notion, it will look kind of trivial and gauge dependent. But let me say, so the analog of this Bondi gauge, it will be AR being zero gauge and AU there is no constant piece in AU. So then the photons will be described by just a component of a gauge field at infinity. So that will be functions of U and V, which will correspond to the polarization of a photon. And originally we have a gauge transformation of this form. But now, if you want to preserve this analog of a Bondi gauge in Maxwell's theory, you kind of left up with the gauge transformations of this form where epsilon depends only on Z. So one would say that this gauge transformation look like just some leftovers of big gauge group, and maybe we didn't quite fix the gauge completely and stuff, but apparently these things are actually observable, and you can design some memory-like experiment to actually observe this leftover phase EM squared plus. So, okay. So now the next step would be to convince you that J0 has something to do with gauge transformation. So with asymptotic symmetries of this type. Okay, let me. Okay, I can erase this whole part. So. Okay, and for the sake of time, I will just mostly outline the derivation, and I may skip some steps, but you can always stop me and ask for detailed questions. So let me write Sof theorem in some nice basis. So let me introduce some bases of scattering states, which I just will be parameterized by momenta and some other scattering data for particles. And then this on-shell amplitude is this particular on-shell amplitude is just matrix element within some in-state characterized by ingoing momentum, and some out-state characterized by outgoing momentum. So that's my diagram. So then insertion of additional soft graviton, we can just put an outgoing graviton creation operator. So alpha will label plus minus, just label to physical polarization, and we also have Q, so the graviton momentum. So, and that's basically this thing in the limit Q goes to 0. Is basically given by this J0 times the same bracket without graviton insertion. Okay, so when I formulate this gauge transformation, I kind of formulated everything in a local way, and here everything is on shell, so I need to use some mode expansion, which will relate me local fields with their mode expansion. So, and that's as given by a following expression. So alpha labels polarization. Okay, and I have some factors. Okay, and here some alpha, Q. So let's hopefully do the longest formula. Okay, so now on the right hand side of this expansion, I just have some linear combination of stuff with A of Q. So that's why I can use this formula. I can combine these two expressions, so I can like literally substitute the let me call it AA0, which will be just limit R goes to infinity of AA. So 0 means radially independent. So let me insert the following. And limit omega goes to 0 is something like taking a time integral. And if you get into details, you can notice that if I insert the following expression, so it's function on. Okay, I need to. So q square equals 0 means that q can be written in the following form. So there will be some energy which goes to 0, then 1, and here I will have just a unit 3 vector which is parameterized by a point on into sphere. So this hat is basically embedding of R2 into R3. So that's why I can trade 4 momenta at the limit q goes to 0 to just a point on the sphere. So this insertion in between in and out state will just give me the following expression. So let me also say that I'm working in this complex coordinates. So then a lot of stuff will be easier. So if I insert a z bar, apparently here I will have some expression of this type. So all my external particles are also massless, so I can do the similar trick for them. So I can parameterize their direction of momenta by some point on the sphere. So literally I will get up to some coefficient which I dropped. I will have expression like this. So that's what you will get if you just substitute this epsilon, like when you substitute AA by this expression into S matrix, there will be some trace over these polarizations, and there will be some polarization tensor. But after you print everything, you end up with this nice expression. So now it's easy to see that if I apply, so that's function on a sphere. Okay, so let me call it the A, just not to miss this. It's not just a holomorphic function. So if I apply okay, let me see. Sorry. If I apply dv bar to this whole expression, apply dv bar here, I will have a bunch of delta functions. And bunch of delta functions is nothing but some local action of charge on external particle. So this expression is the same as acting with some charge operator on my external particles. So something like this. I can define QH. Okay, sorry. Let me do one more step. So then I have a bunch of delta functions. I can just integrate.
That's a sum over the out and in particles, no?
Yes. So it's sum over out minus sum over in particle. Yeah. Okay, so if I multiply by epsilon of d and integrate everything, this delta function will turn into a simple combination. And this is nothing but just a phase transformation acting on external data. So this thing acts exactly like u component of the current integrated on some limit that goes to infinity. I just take u component of the current on some Cauchy slice, on some u equals constant Cauchy slices, and then push this to infinity. So that this expression is really integral on Cauchy slice with Cauchy slice limit taken to infinity. So this right hand side is nothing but epsilon. So what we obtained here the following relation, that if you insert just electric charge operator into S matrix, it gives the same effect as inserting certain zero mode operator. So now you can use Maxwell's equations, which hopefully I didn't write. So for Maxwell equations, there is some new component of Maxwell. I think I will write it because. So I can look at U component of Maxwell equations. So I will have the same JU as JU here, and I will have a couple of other terms from this expression. So I will have a term which is like this, du FUR, which is literally a radial electric field, and I also will have some terms of this type. Which will exactly correspond to a soft insertion. So here I'm acting with dz bar on just the component, so I can replace it to a normal derivative. So literally now, if I just multiply by epsilon and integrate over the whole scribe, both left-hand side and right-hand side, I will literally see that this particular linear combination, if you are careful with all signs and coefficients, that linear combination of JU integrated with epsilon and exactly this zero mode contribution integrated with epsilon will combine nicely into what we call local charge expression. So let's integrate it over scribe plus, and since epsilon is U independent, so this whole thing is a boundary term. So it's literally FUR epsilon integrated over sphere scribe plus plus minus the same expression integrated over sphere at scribe plus minus. So that's in my diagram. Scribe plus plus, it's this two-dimensional sphere and this scribe plus minus. So it is possible to impose boundary conditions in such a way that there are no charges which survive to a scribe plus plus, which is a natural condition if you just consider a scattering of massless particles. To just have massless in going and massless out going, so no charges remain. And therefore, we end up with some statements that if you define some charge Q, which is epsilon FUR, okay, you need to be careful that you need to define charges actually separately from scribe plus and scribe minus. You need to define Q plus and Q minus. Okay, and generally, okay, there will be two functions, some epsilon and epsilon prime. But then you can do a matching procedure in such a way that you relate both FUR and FUR across the scribe plus, which uniquely fixes some relation between epsilons. And then what you will end up is this expression, the following expression. So in between any in and out states, Q plus S minus SQ minus, just given to 0, and since it's true for any scattering states, you can say that Q plus S minus SQ minus is 0, which tells you that this Q is a symmetry of S matrix. And if you look at how this Q acts on gauge field, so if you look like Q plus a commutator, you will see that action is exactly dA epsilon. So that's why it's connected precisely to this particular asymptotic symmetry. So in case of gravity, all this derivation can be like simply generalized to a gravity case, but some expressions will have more complicated tensorial structure, but sort of the whole logic remains the same, that for a certain good enough zero mode, if you act with some differential operators, you will get a bunch of delta functions on the right hand side, and you can integrate against some function and get the local action. Yes?
Yeah, where exactly did you put in, as far as I understand it, a theorem like this can only work if you have massless charged matter, because this is sort of saying that again, like the momentum in Andy's talk, that locally the charge going in here and the charge coming in here at the corresponding angle is conserved.
Yep.
And that can only happen if you've got a lot of soft charges that can go off, right?
Yep.
Okay. Where did you put that in this derivation? I just didn't. It went.
So in this derivation, the crucial part was getting this delta function. So in case of massive particles, you will just have some expression which wouldn't localize at a point zk. So you can still do something like this parameterization, which will be more complicated for a massive particle.
Sorry, massless.
Charged
or
okay.
Massive charge.
Charged.
Yeah. So for massive, okay, there are a couple of assumptions for which massless was important. So firstly, this parameterization is not quite clear. Like how far you can do with a massive particle, because you can choose different frames, and in some you can choose some frame where one of the particles will just sit there, and then it's not clear what is the direction of momentum. So it's not clear like how to properly define all the case. And the second thing which was crucial is this local action. So in case of massive particles, like you will have some expression which is not delta function, which is kind of agrees with the fact that massive particles can't reach scry. So that's why you need to cancel a real particle contribution like this Ju contribution. So this whole current J reaches scry, and that's why you need a whole bunch of soft stuff to cancel this contribution from Ju. So for a massive particle, the situation would be very different, because this J wouldn't reach stride, so you wouldn't have a delta function at exit points.
And you also have this extra term, right?
Which exit?
The one you crossed out.
So this one, and you need to be careful with what you're going to do with boundary conditions, like how you're going to eliminate some charges which may just stay there.
But the usual low energy theorem doesn't assume massless.
Yes. So this form of Weinberg-Soft theorem is perfectly good for both massive and massless case. So Andy had some idea of how you can actually generalize this whole procedure to a massive case, and hopefully he will write a paper on it. So we will all. But it seems that it's not that impossible to somehow twist this picture a little bit to include massive particles as well. So,
but they don't get up to null infinity, really, massive particles.
Exactly,
Yeah.
right. So
You have to
what
include
happens is there's a
infinity.
component of the current that goes up. If I take any finite causal diamond, okay, then on the null boundary of it, a massive particle will go through it if it's big enough.
Yeah, you have
But
to.
there's a component of the current that's going up towards the top, and it ends up that the momentum ends up at I plus rather than scribe plus.
That's it.
Right. So it's somehow that's missing from this, this
So,
derivation. But I just, the points that he pointed out were the points I was missing with where was this being put in, and now I see it.
So for this derivation, there are a couple of steps where it is crucially important that the particles are massless, and it kind of nicely fits with the idea that we want to define scattering matrix in like Minkowski space, and you have some data on scry minus to a data on scry plus. So you can include like both gravitons and the massless particles in this scattering problem. And it's
once you take loops into account, of course, these scattering amplitudes don't exist, right? Massless charged particles.
Yeah.
Problem. So that's why I say that
Not with gravity.
Yeah. So you can do the gravity.
Well, no, also with gravity.
No,
there's an issue.
no problem.
What?
No problem with massless particles.
There are no collinear divergences, but there are still amplitudes where massless particles go off in all
You
directions.
have to do block-Nozick.
Block-Nozick doesn't define amplitudes; it defines inclusive cross-section.
Yeah, that's what we have to talk about.
My technicality.
What he's talking about.
You're not doing loops.
Let's not interrupt his
so
talk
this
anymore.
discussion
I'm sorry.
was purely classical. So I agree it would be interesting to see what happens at the loop level. So the good part about this leading soft theorem that it was classical and quantum, so there is no room for correction to it because it has some like as big pole as possible. But J1 generally has some infrared corrections, and it's you need to be careful what to do in that case. And I don't have like much intuition of what happens at the quantum case with J1. So now let me hear.
But may I just ask, can you do two soft photons?
I think you can include two soft photons, and that's kind of crucial thing which you need to do in Young-Mills case in order to see some actual interaction, in order to see difference between Young-Mills and Maxwell, and that's what was done by Andy in a paper with Temple and Prahar. I think it was some recent paper. So
can you see factorization in this language?
I think I'm sort of not ready to discuss multiple soft limits right now. Yeah, okay. But something was done in this paper by Andrew Harvey. So we can probably discuss it after it. So in the gravity case, all these formulas they kind of nicely generalize. So all these charges like Q plus charge, you just replace FUR, which is literally a radial electric field, to a Bondi mass, which is exactly this one here, or I would say better Bondi mass aspect, because this MB generally depends on the angle, and what we usually call Bondi mass is usually integrated on the sphere. And sort of one kind of side note, which usually is very controversial also, that really when you have this asymptotic symmetries, you can ask a question whether there is some kind of conserved quantities which do correspond to asymptotic symmetries. So since it's not exactly symmetries, there are some subtleties with this quantity. So basically here the statement is the following, that you can define some notion of electric charge at null infinity, and the notion of this electric charge will be just a flux of radial component of electric field. So that's what you can measure if you just sit here on a sphere at null infinity. So you can choose some small region on your sphere and just measure flux of electric field to this region. And basically the statement is that if you define your electric charge in this way as a flux of ER through your part of sphere, then this charge is conserved through a scattering process. So that's a kind of analog of conservation law which corresponds to a symmetry. But since asymptotic symmetry, you need to be careful with the notion of a charge. That notion of a charge should also be properly suited to your kind of asymptotical setup. And in case of gravity, this notion is you just measure Bondi mass at given angle. Yes?
You're not at higher dimensions yet, so I think you're
yes.
But in higher dimensions, the Bondi mass aspect, what you call this MB of that there, that's really but not the leading term in the du squared, but it's sort of buried at higher, it's at higher asymptotic order. It's not the leading one, and the ones that come before are not purely kinematic. So they're not just so like in. So how do you deal? Maybe you can come to that question.
Okay, so in high dimensions, So in high dimensions, like Bondi mass will sit in some term like this.
Yes.
So that's what we will call normally a Bondi mass.
Yeah, but it's not the leading.
It's not the leading. Yeah, but it's still a quantity. So basically, this expression tells me with this commutator tells me that really this radial electric field is conjugated to this zero mode of A. So I can say that my AA at infinity is like some pure gauge DA phi. And this commutator basically tells me that these two quantities just canonically conjugate. And you can see this from just writing some canonical symplectic form and massaging it a little bit. So I'm saying that the zero, if you define the zero mode of CAB, which will be super translations in higher dimension, that they will be conjugated to a proper Bondi mass. So and this extra suppression factor came from when you write a symplectic form, you will have extra r to the d from a volume factor, and that's why this thing which kept fixed in arbitrary dimension will naturally be conjugated to a correct Bondi mass. So that's why it is still correct Bondi mass conservation, which is conjugated to change in CAB.
See, remind me, how physically do you get the terms that are leading above this? Do they, or should you set them to 0?
No, somehow what happens is that if you compute the mass integral, all these terms turn out to be total divergences on the sphere, so they just integrate to nothing. But that uses really Einstein's equation. It's not so obvious that it actually happens. So I don't think it's not so clear what they correspond to, but they're not just kinematical, like that they would be the same in every asymptotically flat space-time.
And they aren't just, gauge, I guess.
No, you can't gauge them away. No.
Okay, so now apparently this procedure with some minor modification can be carried through for a subleading term. So the minor modification will be of the following form. So firstly, you need to add some additional power u here. So it's some different zero mode which will conjugate it to a charge here. And really, if you look carefully at what happens when you do a Fourier transform, when you do this Fourier transform, you will see that u du will be Fourier transformed into something like, so I call it omega q here, the omega q plus 1. So this operator will exactly project out 1 over omega q pole. So at the right-hand side of this expression, you will have a pure J1 instead of some mixture of J1 and J0. So for a right zero mode, and apparently for the zero mode, you need to apply this dz bar derivative twice. And here you will have some, instead of this just a delta function, you will have the following expression. So it will be some dz bar of a delta function d minus dk times. Okay, and you also need to be careful that when we go from J0 to a J1, we lost the power of p. And therefore, here we have exactly conservation of ek divided by ek. And that's why it was just qk times delta function. But now, since we are one power down, you end up with just one over energy here. So, and you will also have other term which will be of the following form. So it will be delta function of d minus dk multiplied by 2k, and here will be vector. So now it is vector field in zk because I can write the angular momentum part of j as some kind of pd over dp minus vice versa. So that's why I turn it into some differential operator acting on this zk. Okay, so now so that's what happens in the gauge theory case. So in the gravity case, the situation is slightly simpler because you really have 2 powers of energy and you just lost one. So in a gravity case, like this thing will be simplified into some simpler looking expression. And then, okay, if you integrate against some arbitrary vector field on a sphere, yeah, so what you will get the following, that the operator which you will get from a soft theorem acts on a state parameterized by E and Z. Okay, sorry. I wasn't careful enough. Sorry.
Are you writing, are E and omega the same thing?
No, omega is momenta for soft particle, and E is energy for external particles.
Ah, okay.
Yeah, so E kept fixed and omega goes to 0. So, okay, so in a gravity case, the answer will be like this. Okay, sorry, messed up this powers a little bit. Okay, but still there will be like some fancy 1 over E in denominator. And then from this expression, you can recognize it's, so when we look at its action on particle with energy E and momenta Z, you will see that the action is the following. So there is a usual Virasoro transformation. Okay, there is also a complex conjugated part, and another term will be something like a conformal weight part. So this E d over d just measures some proper conformal dimension of a field as you approach scribe. But this part is just the usual Virasoro transformation. So that's what called action on a state with energy E and direction of momenta Z. And plus complex conjugate.
What goes wrong when you try this at the next order, second subleading?
So if I try to a second subleading, then I will have some fancy 1 over E in denominator. So that's kind of a problem. So let me try to explain it in context of Maxwell theory. So when I look at this operator, they nicely form a closed algebra which are just some Virasoro acting on fields with certain weight on a sphere. But if I start looking at the commutators here, so if I turn this thing into a differential operator, I will have something like this. So it will be UK something like dYz d over dEk. Let me assume that I have just a single particle plus something like Q over E d over d. So now if I start commuting these operators, I will get some infinite dimensional algebra, because each time I will hit like d over d to E, I will get like smaller and smaller powers of 1 over E in denominator. So, and the same thing kind of happens if I look at subleading term in a gravity, that I wouldn't have any powers of Ek in the numerator to cancel this contribution from angular momentum. So I will have necessarily some 1 over E and some d over d pieces, and this whole thing will still produce some strange infinite dimensional algebra. So and it's still not clear what to do with this infinite dimensional algebra even in gauge theory case. So that's why we sort of didn't touch in gravity before we can understand what happens in Maxwell. But that will be a source of a problem. That there will be some 1 over E which are problematic in this case.
Is it possible?
You said Virasoro here. Do you get the full Virasoro algebra or just the conformal subgroup from this subleading thing?
Conformal. Oh, okay, maybe.
Just the
Infinite dimensional or SO?
Yeah,
just SO1 comma 3 or the infinite?
No, infinite dimensional. Yeah.
It's the infinite dimensional.
But don't these have singularities?
Yeah, so that's
why they usually discard. I mean, in the
Well,
old
these are
fashion way.
infinitesimal. They're fine.
So on one hand, they're kind of infinitesimal. So you may say that but there are some singularities or some problems of a different type. So if you look at how these transformations act on for example, the z component of a metric, then the super translations were acting in a very simple way. So it was something like dz square epsilon. So just. But if I look how Virasoro acts, it acts in a slightly different way. So you see that there is some fancy u prefactor in front of dz cube yz. So basically, it's not only some singularities on a sphere, but really this metric in a Bondi gauge, it is somehow divergent as you approach as u goes to plus or minus infinity. So it's still not clear like what to do with this transformation. On one hand, they kind of nicely fit with the subleading Weinberg-Soft theorem. So it seems that they might be useful for something. But I agree that if you try to precisely to do some mathematically precise definition of this conservative charge, then you will run into some trouble that if you go through this procedure, then conservative charge will look like something like this. So yz, and here it will be called nz minus where nz is some 1 over r piece in this. So that's what people usually call angular momentum aspect. So, and this expression, it's not obvious that why is it finite and whether there is some theorem that for some sufficiently nice asymptotically flat cases it remains finite or something. So this expression was much nicer because there were a lot of positive energy theorems and other statements which allow you to keep it both, which allow you to keep this expression finite. But this expression is not clear whether it's finite or infinite because of this like naive u goes to infinity diversion. So there are some problems in kind of trying to carry out this whole correspondence to the very end to something like conserved quantity in gravitational scattering. So like locally you kind of get Virasoro symmetry, but then when you try to fit it into some gravity framework, you run into some trouble that certain quantities diverge or not well defined. So
you're saying that you did actually get, because what I remember we were finding were the subleading terms were sort of their rotations with an extra hole in, but they're not actually homomorphic on the sphere, so it weren't actually Virasoro. So we got a sort of 1 over p dot k times a rotation, and that's not actually holomorphic on the p sphere. It's in 4 dimensions. It's
you're saying that this yz shouldn't satisfy like some form of history?
Well.
So you're saying that you don't need like the condition like this, or what?
Yeah, we did. Well, we got a factor that wasn't holomorphic as well. I think. I thought it wasn't quite Virasoro, but maybe you were doing something slightly different.
Okay. Let me comment on this issue. So, I think the sort of my understanding works in the following way. So really, if we look at the Weinberg-Soft theorem, we basically have so far we explored dependence of this soft factor on direction of momentum. So that's where we get the sphere, because this null momenta naturally parameterize the sphere. But we also have Weinberg-Soft theorem for 2 physically independent polarizations. So here we actually have like 2 statements for 2 different epsilons. But when we end up with asymptotic symmetry, we just get with a single charge, which is it's local charge in the sphere, but a single function. So it was parameterized by a single function epsilon. So what we really did, we just turned some linear combination of Weinberg-Soft theorems to be into asymptotic symmetry. So in case of subleading soft theorem, I think Weinberg-Soft theorem is kind of still bigger than the symmetry group. So at least it's parameterized by something like 2 vector functions on a sphere which are not necessarily goal-morphic. So that's so far kind of the formulation of Feinberg-Soft theorem allows you to kind of extend this asymptotic symmetry even further, but it's not clear how to embed this into a normal gravity description. So what is a gravity setup which allows you for even bigger symmetry? So in case of twistor symmetry, it might be possible just with tricky formulation, but if you do just a normal jar formulation.
But you already have problems with the Maxwell theory, right?
So Maxwell theory, there are problems of different types that algebra do not close, and it's some kind of infinite symmetry, and it's not clear why the commutator should also be
J1.
Yeah. So with the Maxwell, it's even more complicated problem. But
can I ask another question about that theorem? So you very quickly said, oh, there's this orbital angular momentum term, and then really only orbital plus spin are conserved, so it has to be spin. But if you're talking about the coupling of the photon to spin, there's a question of what the gyromagnetic ratio of the particle is. And again, these theorems, we're sort of... No, the gyromagnetic ratio does affect the second term, I believe. And I don't think it's universal. And then there's a whole other story with looking at the high energy behavior of amplitudes that tells you G has to be equal to 2 to lowest order in electromagnetism. But that's not the soft theorems. I think this term in the soft theorems, if you just actually calculate it in a theory where the particle has an anomalous magnetic moment, will have an extra contribution that's not universal.
Okay.
In Maxwell theory.
Well, there's always this theorem is non-perturbative. So there are, there are loop corrections. Any particle is anomalous.
Lowe's theorem was always perturbative in electromagnetism.
Perturbative electromagnetism, but not in
everything else.
Which will produce anomalous magnetic moments anyway.
That's definitely the case.
You're right that the full vertex appears here, but it's not either 1 or 2 or anything.
It's got this order alpha over pi.
There can be other couplings.
Right. So there isn't a universal theorem at that level. The charge.
No, there's universal theorem in terms of the angular.
The soft theorem for J0, all that happens is you renormalize the charge.
No, but in the end, the soft photon couples to the angular momentum. Period.
I think that's right.
Corrected by all the interactions, whatever.
Right, but there's a renormalization of that coupling.
It is
But it's
whatever
still
it is.
I mean, the definition of universal is that there's a nice simple formula.
It is whatever it is. So is the charge, by the way. The charge also has renormalized.
That's
So E there contains all the renormalization.
right.
okay.
So a question, how much longer do you need? There's another talk.
No, I think that's I'm like covered all the problems in subleading house. Yeah, so I'm more or less done. Like, but if you have some questions about like further directions, I can answer them. But I don't think it's a good idea to get into these details unless there are questions.
Can I ask one more question about the subleading things in gravity now? So there is the subgroup of Virasoro, which is just, the Lorentz transformations, right? And is there some piece of the subleading theorem that just involves those, or is?
Yeah. So let me explain it in the following way. So the whole kind of idea was that you really have two contributions. You have contribution from what is called hard particles, which is usually this fancy-looking delta functions acting on just matrix element, and you also have some insertion of soft temperature, of soft particles. But these insertions, they typically have some number of derivatives applied to them, and you can integrate by parts. And for example, for subleading soft theorem, if you integrate by parts, you will this expression so if you integrate by parts, you will get something So if we are dealing with the gravity, then and here we will have some. I think it's integrated, and basically you will have some number of zero modes for this operator, and these zero modes will exactly correspond to Lorentz transformations. So you will have for normal symmetries which are inside the asymptotic symmetry, you don't need to insert all this soft particles. This soft operator just became trivial. More questions?
Yeah. Questions or comments?
Well, I didn't quite understand the statement about the subleading. Is that supposed to be an exact? I mean, forget about asymptotic symmetries. What is the status for the subleading? Is it supposed to be valid exactly?
I think the general statement is that subleading soft theorems may have some
Okay.
correction.
They have they definitely have.
They do have got
Absolutely.
Yeah.
So they don't follow from gauge invariance alone.
But you still have a room that, as I said, so the soft theorem is a statement like for different polarizations. So there might be some special linear combination which is somehow either protected from this loop corrections or have the loop corrections much simpler than we generally expect. So there is still a room that by doing this fancy linear combination you somehow may simplify it, or there might be some proper anomaly which corresponds.
Word identity is exact. This is clear, right? To all order.
If it follows from a symmetry.
I mean, the word identity. For
But I'm saying that the word identity is it's just a subset of Weinberg-Soft theorem. That Weinberg-Soft theorem is definitely is a bigger.
Has a bigger content than.
Yeah, it's a bigger content.
I'm not talking about your word identity. I mean, I'm talking about the one that Francis Lowe was using.
Well, it was.
But there's still loop corrections. I mean, just because. I mean, of
It's
course.
not a perturbative. It's not a perturbative theorem.
No, but
The word identity is exact. Now the way you implement it.
If you look at non-abelian theory, there are loop corrections.
It's not.
Yeah, I think there are general loop corrections to it. So.
Look, in the QED case, I think it's clear that there are loop corrections and that they depend on what the particle is, because the anomalous magnetic moment is different for different particles.
The photon couples to the magnetic.
Yeah, but it's still.
But there is a theorem you can write down for both QED and for gravity, which is true for all order.
For gravity? But
Well, yes, for gravity. That's what.
not for the
The
second
leading
subleading.
theorem, for sure.
And it does.
But not for the second subleading. That gets, well,
Oh, I think
it's a little complicated exactly what happens.
Right.
Yeah, there is a slight difference whether there is a factorization which might be true at all orders, that really amplitude factorizes into a soft vector times hard amplitude, and the more complicated statement whether this soft amplitude, whether it has loop corrections or not. So I think it might be true that generally it factorizes. That's a statement which is true to all loop orders, but this soft factor, it still has some loop corrections. I think that's a statement which is precise. And
Anything else? Okay, well, thank you very much.